Next slide.
The last video in this lecture set is about Earth's special form of tectonics called plate tectonics. Remember that tectonics can occur on any planet or moon, but Earth is the only one that has plate tectonics.
The Earth's lithosphere is broken up into chunks called plates, with densities of about 3 times that of water. Oceanic plates are made of basalts that are cooled volcanic rock made of silicon, oxygen, iron, aluminum, and magnesium. Oceanic crust is only about 6 kilometers thick. The continental plates are made of another volcanic type of silicates called granite. Continental crust is much thicker than oceanic crust, up to 35 kilometers thick. The continental plates have densities of 2.7 to 2.8 times that of water, while the denser oceanic plates have densities of 3. The mantle convection causes the crustal plates to slide next to or under each other, collide against each other, or separate from one another in a process called plate tectonics. This process works about as fast as your fingernails grow. Plate tectonics is the scientific theory that describes this process and how it explains the Earth's surface geology. Earth is the only terrestrial planet that has this type of tectonic activity because plate tectonics requires liquid water to solidify the oceanic plates at the mid-ocean ridges where seafloor spreading is happening. And more importantly, the liquid water lubricates the asthenosphere and softens the lithosphere enough so that the plates can slide past or under one another. Venus has enough interior heat to have convection in its mantle, like the Earth, but Venus lost its water. So its lithosphere is too rigid and poorly lubricated for plate tectonics to work.
Next slide. Plate tectonics is a relatively recent theory, having been proposed in the late 1960s and finally being verified enough so that it could be put in the introductory geology textbooks in the 1980s. Remember all the peer review, error correction process that happens in science before something is fit to be printed in a textbook. What made scientists accept a theory about a process that takes place over millions of years, much longer than human civilization? Today, we can easily measure the motion of the plates using GPS sensors, but we didn't have that back in the 60s and 70s. As in any robust scientific theory, there are multiple independent lines of evidence supporting the theory. For plate tectonics, the evidence is continental motion, seafloor spreading, earthquake and volcano locations, and the difference between the seafloor crust and continental crust. For continental motion, we see that the locations of rock types and certain fossil plants and animals on present-day, widely separated continents would form definite patterns if the continents were once joined. For example, the eastern side of South America fits nicely next to the western edge of Africa, and several fossil areas match up nicely at those points of intersection. This picture shows a reconstruction of the continental motion starting from the last time the continents were all joined together in a supercontinent called Pangaea, about 225 million years ago, and then through the time of the rise and fall of the dinosaurs. You can see the small piece of the Indian subcontinent ramming into Asia to make the modern-day Himalaya mountains. Geologists have been able to trace the motion back to the previous supercontinent of Rodinia about 1 billion years ago. The cycle of supercontinents, then breaking apart and then rejoining, has happened several times in Earth's history. Another very important piece of evidence is seafloor spreading. There is an immense submarine mountain chain that zigzags between the continents and winds its way around the globe. At or near the crest of the ridge, the rocks are very young and become progressively older away from the ridge crest. The youngest rocks are at the ridge crest always have the present-day normal magnetic polarity. Stripes of rock parallel to the ridge crest alternate in magnetic polarity as the Earth's north and south magnetic poles switched positions. Normal, reversed, normal, etc. Alternating stripes of magnetically different rock are laid out in rows on either side of the mid-ocean ridges. One stripe with normal polarity and the adjoining stripe with reversed polarity. This happens when magnetite in molten rock at the ridge aligns itself with the Earth's magnetic field. When the molten rock with the magnetite hardens, it freezes the orientation of the Earth's magnetic field at that point in time. The Earth's magnetic field has flipped its polarity many times, with a cyclic average of about 300,000 years, but with a wide range of times. Some switches happened a few tens of thousands of years apart, and others several million years apart. The most recent long-lasting polarity switch was about 780,000 years ago, but a more recent one, 42,000 years ago, lasted for just 500 years before it switched back to what we have now. When the Earth's magnetic field changes polarity, newly rising molten rock at the ridges will have its magnetite aligned accordingly. New oceanic crust, forming continuously at the crest of the mid-ocean ridge, cools and solidifies and becomes increasingly older as it moves away from the ridge crest with seafloor spreading. The result will be a zebra-like striping of the magnetic polarity in the rock that parallels the mid-ocean ridge. The third piece of evidence is that the locations of earthquakes and active volcanoes are not random, scattered all about like you find on other planets and moons. Instead, they are concentrated along areas thought to be plate boundaries, the oceanic trenches and spreading ridges. The fourth piece of evidence is the two different types of crust. The seafloor crust that is less than 200 million years old and is thinner and denser than the continental crust that has a wide range of ages of up to 4 billion years old. The seafloor crust has a density of 3 times that of water, while the continental crust has a density of 2.7 to 2.8 times that of water. Earth is the only place in our solar system with two different types of crust. Next slide. At the top of this slide is a map of the plate boundaries today with arrows showing the direction and speed that the plates are moving with respect to each other. The shortest arrows are about an inch or 2 centimeters a year, while the longest arrows are about twice that speed. Places where warm rock from the asthenosphere rises along weak points in the lithosphere can push apart the lithosphere on both sides. These places are at the mid-ocean ridges, such as the Mid-Atlantic Ridge that bisects the Atlantic Ocean, and the continental rift zones, such as the East Africa Rift Zone. Seafloor spreading causes the Atlantic Ocean to grow from a thin sliver 100 to 200 million years ago to its present size, and now continues at a rate of about 25 kilometers per million years, or 2.5 centimeters per year, which is about the rate that your fingernails grow. Over billions of years, this amounts to huge changes. This pushing apart of some plates from each other means that others will collide. The oceanic lithosphere is cooled by contact with the ocean water. When oceanic crust runs into oceanic crust or into continental crust, the denser lithosphere material slides under the less dense lithosphere material, eventually melting in the deepest layers of the mantle. The region where the lithosphere pieces contact each other is called a subduction zone, and a trench is formed there. At the subduction zone, the right combination of temperature, pressure, and rock composition can create small pockets or fissures of molten rock in the solid asthenosphere that then rise up through cracks in the crust to create a range of volcanoes. An example is the Juan de Fuca plate along the coast of northwestern United States, subducting under the North American continental plate to create the Cascade volcano range. This subduction process can have a profound effect on regulating Earth's climate over long timescales of hundreds of thousands to millions of years. When two continental pieces bump into each other, they are too light relative to the asthenosphere and too thick for one to be forced under the other. The plates are pushed together and buckle to form a mountain range, such as with the Indian subcontinent ramming into the Eurasian plate to make the Himalayas. Plates can also slide past each other in what's called a transform fault, such as the San Andreas Fault in California or the Anatolian Fault in Turkey. At the bottom of the slide are some of the positive effects of plate tectonics. Now, of course, when we experience the effect of plate tectonics called an earthquake, that can be very deadly and destructive, but there are some positive benefits of plate tectonics that have kept the Earth habitable and biologically productive for billions of years. The first benefit is the high level of global biodiversity. There are more different kinds of animals or species of animals on land than in the oceans. There may be more total biomass in the oceans, but there's a greater variety of species of life on the land because there are greater varieties of environments on land that life has had to adapt to. Greater biodiversity means that if something changes in the environment that is detrimental to one species' existence, other species may be able to survive the change. The tiny mammals survived what wiped out the dinosaurs, and they were able to adapt to fill in the environmental holes left behind by the dinosaurs' demise. Without diversity, that is, just having a few species around, an environment change can lead to the wiping out of most of life. The second benefit we've already seen in a previous lecture video is that plate tectonics helps make a global magnetic field possible. Plate tectonics cools the planet's mantle to create a large enough temperature difference between the core and mantle to produce the large-scale convection in the metallic core needed to make a magnetic field. Recall that Venus doesn't have a global magnetic field because it doesn't have plate tectonics. The third benefit is the transportation of carbonate materials to regulate Earth's climate. Carbon dioxide in the atmosphere dissolves in rainwater. The slightly acidic rainwater erodes land rocks, and the broken down minerals are carried to the oceans via the runoff. This weathering process removes carbon dioxide from the atmosphere. Calcium in the broken down minerals combines with the dissolved carbon dioxide in the oceans to create carbonates, such as limestone at the ocean floor. After intense mountain building times in Earth's history, such as the formation of the Appalachian Mountains 300 million years ago, and most recently the Himalayan mountains, the Earth cooled off dramatically because of the increased amount of weathering. Through plate tectonics, the limestone and other carbonate minerals are carried to subduction zones where they are melted. The melted rock releases carbon dioxide through volcanoes. The fourth benefit is the creation of continents and the continental shelves, or places of shallow water. The formation of the limestone happens most easily in shallow water. On Earth, the presence of continents makes it possible for places of shallow water to exist. The continents are created from lower density material than oceanic plates through the subduction process of plate tectonics. Liquid water plays a key role in helping the subduction process of plate tectonics to work by lowering the melting point of the oceanic crust and keeping the lithosphere pliable or bendable enough to bend and descend far enough into the mantle to melt. So there are many benefits of plate tectonics for improving and maintaining a planet's habitability in the long term. If plate tectonics turns out to be a required agent for long-term habitability, that could have profound implications for the likelihood of other exoplanets with life on them in the galaxy.